All right, good morning. Let's start our lecture. So the midterm average is at 73, so that's not too bad, actually. And there are a lot of people get really good mark, and at least I noticed there are 3 students got 100%, and there are a number of students got over 90%, so that's a pretty decent performance. Okay, I'm happy about that. But still, there are some students who didn't do very well. Okay, yeah. My practice always at this stage is always a warning, actually, for the final exam. Even though that you have done really well in the midterm, but I have seen many cases that basically students who did well in the midterm and then flunked in the final exam. The reason I can tell you why, because final exam is always comprehensive, and not because the question becoming more difficult, just because you don't have enough time to prepare for the final exam, just like the time you spend on the midterm. In particular, this year, our final exam is the first one, December 4th. So for our section, ends of Thursday, for their section Friday. So literally, basically after the weekend, then you basically get onto the final exam. And our exam content will always cover until the last lecture. So that's basically a huge heads up. You're not gonna try to lose the steam or take a break or anything, right? Right now, you gotta basically keep on going. This is as a matter of fact, the last couple of weeks of this course will be the highlight of this course. A lot of questions, obviously a lot, but at least a couple questions of the final exam will be from the last week of the lectures. So just give you warning of that. And if you did well, excellent. Keep doing what you're doing. But if you're not doing well, ask yourself what happens. Right, and I'm always there. If you have questions, feel free to come ask us, ask me or the TA. So, bottom line is, this is a good time to do some self-reflection. Okay? So we make sure we all do well in the final exam. Okay, and in typical, the average final exam is always lower than the midterm exam. So my course, typical final exam average probably in the 60s. Okay. So that tells you basically you'll pull down the average for most of the students, right? Okay. The question marking, and I did the first one. Dr. Klukas did the second one. We have a TA did the third one, and I did the fourth one. So if you notice any significant discrepancy from what you expected, or any obvious mistake in the marking. Okay, so something like you did it, but then we didn't notice. Feel free to come to me and let me know. Okay, if there's no significant difference, I try to discourage people to come to my office asking for 1 mark or 2 mark. Right, that's really making no difference. Okay, but feel free to come if you have any questions regarding final exam. Unfortunately, I won't go through the final exam. I won't go through the midterm exam in the class. And if you wanted to know the solution, and I'll be happy to go through with you, okay, because of the too many things to cover. Okay, so any questions so far? Okay, yeah. So double check with the mark posted on the canvas with the one that you received here. If there are any data entry errors, let me know, and we can always change that. Okay. Okay, so let's do a quick review on double integrals here, and then we'll continue on the topic of double integral using polar coordinates. Double integral is about this formula here. Yeah. So integration integrate this function f of xy with respect to the region R. So that's basically what this double integral is about. You have a function which we can graph it out, which is surface, and you have a region R which is in the xy plane. So basically what we're trying to do is we're integrating this function over this region R. Then the idea is integration, right, is always about scan through this region R, just like a single function integration. So So you're scanning through the range from A to B. And here we're trying to scan through this region R. Okay. Now when do the integration, there's two orders, dxdr or dxdy or dydx. So order matters sometimes, but you have to choose an order before you can get started with the integration. And the second question you got to ask is, how do I scan through this region R? If you choose, let's say, dy dx, okay, then the way to scan through the region R is you draw narrow lines, okay, in the positive y-axis first. Okay. Essentially, the first step you do is you create essentially a green line segment, and then we scan through this region R. Okay. Basically without any redundancy, so cover every corners. So that's what we call integration, right? Oh gosh, okay, good. Okay. All right. If you do the other order, you do very similar steps. You draw an arrow line in the x-axis, and then you sweep through this region R to find the limits. Okay. Now, in previous lecture, we also started to do the double integral. Okay. For some questions, it's probably easier, okay, to use a different coordinate system. In particular, the one we're talking about here is the polar coordinates. Okay. So polar coordinates basically means instead of describing the coordinates of a point P using x, y, and we use another set of coordinates, which is r and theta. Okay. So r theta here is what we call the polar coordinates. And the relationship between r theta and x and y fairly straightforward. You can literally just derive the coordinates x and y using r and theta. So x equal to r times cosine theta, and y equal to r times sine theta. Okay. So that's the relationship between polar and coordinate and the Cartesian coordinates. Now always remember, r is basically the magnitude from origin to the point P, and theta is the angle between the vector r or the magnitude r with respect to the x-axis. So it's always counterclockwise is your theta here. Okay. So now the question here is basically how do I conduct a double integral using these polar coordinates at here? So here's what we're going to do. Okay, here is my original double integral at here. Okay, so this is original double integral in Cartesian coordinates. Okay, now dx dr at here. This is essentially the dA or dy dx, okay. And this is dA at here is what we call, right, a differential area. And if you recall that when we get the dA, what we typically do is we grab a small rectangular area, okay, within this region R, and we call that dA. Okay, that's how we basically model this double integral formula here, right? Okay, so now if I wanted to conduct everything using polar coordinates, apparently I'm not going to use x and y anymore. So the simplest thing I could do is I'm going to replace the x and y here with this r cosine theta and r sine theta here, right? So that's direct relationship for x and y at here. So x, I'm going to replace that with r cosine theta, and y I'm going to replace that with r sine theta. So that function f of x, y, okay, whatever function it is, originally is x and y in terms of x, y. So now I can change everything in terms of r and theta now. Now the tricky part is dx dy here, or the dA at here. So in order to do the integral, so I'm not going to use dx dy. So we're going to use, of course, dr d theta, right? So that's the idea. Okay. Okay. So, but the question here is, okay, is it going to be just simply change the dx dy to dr d theta, or is there something else actually we need to add it over here? Okay, so that's the question mark at here, right? So let's find out what will be the change, okay, for dx dy, okay, to dr d theta. What do we need to put it over here? Okay? So this is the idea. I'm going to follow the idea of Cartesian. So in Cartesian, and just recall that here's what we do, right? And this is if this is your dA. So what we do is we essentially create a rectangular area, and this side is dx and this side is dy, and then this is your dA, which is dx times dy, right, or dy times dx. So we create a very small differential, small rectangular area, okay, with dx dy as the two sides. Okay, so that's the small area. So how do I create this kind of small area in Cartesian coordinates then, right, or in polar coordinates? So in polar coordinates, okay, so this is how we create that small area now. Here is, let's say, still your x, y, but however, okay, we're not creating the rectangular area. So maybe I should come back here. Now you see how this is created, because see, well, how we draw is we draw two vertical lines in the y-axis direction, we draw two horizontal lines in the x-axis direction. Basically, you create this small area by drawing lines that's parallel to the Cartesian coordinates axis, right? So you draw two lines parallel to this, two lines parallel to that, you create that small area. So in polar, if you recall that, the axis here, one is actually this way, pointing to that vector r direction, and the other one pointing to what? If you recall that, pointing to the theta direction, because theta is rotating basically, right? That's the two new axes in polar coordinates. So this is how we're going to create our small patch in polar coordinates now. We draw essentially two lines, okay, in the direction of the r, or the r-axis, er-axis direction, okay, and then we also draw two, okay, a circular kind of curve which is in the r direction, theta direction, okay. So this is like going in a theta direction here, okay, yeah. And now we have our small patch, right, in these polar coordinates. Okay. So apparently, here's what we're going to do here. Consider this is a circle, right? This is a part of the circle here. So I draw two circles here, and this is basically like the radius, okay, along that circular reading direction. Okay. Then I'm going to call this is r. Okay, so this is r direction. Okay, and the second one here, I give it a direction, give it a small segment, I call it delta r. So increase from r by a small segment of delta r. So from here to here, right? So this is all part of the radius basically. And similarly, I call this is theta, and this portion I will call it delta theta. Okay. So this is essentially very similar analogy to this. You got a dx dy here, right? So if this is x, this is y, so you increase the x over here by dx, increase the y to here by dy. And here we have r, increase r to delta r here, and then theta by another delta theta. Okay. So now let's take a look at what is this area for the small patch at here. This is just, I draw it to exaggerate a little bit, but you can consider this is a very small delta theta, very small delta r. Then in essence, then this little area, even though this side is curved, but if this is very small, then I can still consider this a rectangular area. Okay, still consider rectangular. So if it's rectangular, we have two sides. One side is this, another side is this. So this side is fine, this side is delta r. Then for this side here, for this side, okay, what's the length of this side then? Right? The length of this side we can calculate using the arc length. So if this side is r, radius r, and then angle is delta theta, then the length, the arc length of this side, if you recall that, what would that be? The arc length of this side. That's right, arc delta theta. Okay. So now, if I consider everything here as a rectangular area, then the area of this patch is r times delta theta and times delta r. Right? So that's your small area dA now, equal to r times delta theta times delta r. That's right. I should use this right now. I should use this. Delta A is approximately r times delta theta delta r. Okay. If we let the delta go to d, so basically make it small, differentially small, and then the delta becomes d, and so becomes r times dr d theta. Okay, so there we go. So in the polar coordinates, if you have a small patch, like you draw like this, then the dA is r dr d theta. So if I go back to my formula here, so that question mark right here is basically going to be replaced with r. Okay? So in summary, my double integral in polar coordinates will become f r cosine theta r sine theta, and then r dr d theta, and with respect to a certain region r. Okay. More precisely, this r right here, sometimes it can be different, but we'll still use the original region r here. Okay. Yeah. Okay, so that's the formula for double integral in polar coordinates. Good? Yeah. So this is the formula, and the next natural question will be, how do I evaluate this double integral in polar coordinates? Evaluating basically means, how do I identify the integral limits for r and theta, just like we identify the integral limits for x and y, right? So let me go through the procedures, general procedures for finding limits for polar coordinates. I'll use a sample area to demonstrate the steps for finding the limits for the polar coordinates here. Okay. Yeah. So step number 1, you need to be able to sketch this region R, okay, and label the boundaries, okay, if possible. So the question may be, I won't present you with the region R, we'll present you with a description of the region R. Okay, bounded by this function, that function, okay, this is basically boundaries, right? So let's say, for example, if I have a region R like this. So this is our integral region R, bounded by y-axis and x squared plus y squared equal to 4, okay, and y equal to root 2. Okay, so 3 boundaries for this region R. So the first step, you got to be able to sketch that. So you look at the three boundaries here, do a rough sketch. Y-axis, that's fine, so that's already there. So this is part of the boundary. Okay. And then x squared plus y squared equal to 4, and y equal to root 2. Maybe let's draw the y equal to root 2 first. So let's see if this is root 2 over here. So basically you draw horizontal lines, and that gives you y equal to root 2. And then draw the x squared plus y squared equal to 4. That means it's a circle with a radius of 2. And label 2. So 2 is greater than root 2, so it's above root 2. And then you draw a circle. Okay. You can draw just part of the circle here, and then that's your region R here, right? So good. So let's use this region to demonstrate how do we find the integral limits. Okay. If we're going to integrate a certain function over this particular region R. So the second step to find the limits, okay, in general, the integral order, so you could be dr d theta or d theta dr. So there are also two different orders set here. But in most of the cases, okay, maybe 99% of the cases, the dr d theta is probably the order that you would go through. Okay, yeah. Not that d theta dr won't go through, but over 90% of the question, dr d theta is probably the easiest way, the easiest order here. So I'm gonna basically using this dr d theta as the order, okay, to demonstrate this finding the limit, the procedure finding limit. So first, we're finding the R limits. Okay. So finding the R limits, here's what you do. Okay. You draw a reading line from origin through region R. Through the region R here. So what does that mean? Basically, starting from origin, you draw a reading line, okay, across this region R. Okay, so you have the region R here. You don't draw it anywhere outside the region R, so just draw it across the region R here. Okay. So you look at the drawing that you just made, then there's definitely going to be a first contact point, which is over here. Yeah. And the first contact point will give you this so-called R mean. Okay, so minimum limit for the R. And the second contact point will give you this maximum limit, okay, for the R variable. And so that's your second contact point. Right? So there are two contact points here. Okay. Now the question here is, what would be the expression for R mean, and what would be the expression for the R max? Okay. Yeah. Now this sometimes require in a lot of this kind of questions. Sometimes you require very simple trigonometry at here. But let's deal with the easy one here, right? Let's deal with the easy one. Let's say, what is the value for R max for this particular case? 2. That's right. So because it doesn't matter where you draw it, right? You draw it here, you draw it over there. Second contact point always fall onto the circle boundary, and that gives you basically from here to here, which is R max. That's your 2 for the radius. Okay. So this portion, just label, this is R mean, okay, yeah, and the other portion is the R max. Okay, so I'm gonna know it's too basic. Okay. Okay, so let's look at the R mean, right? The R mean I find is particular for this kind of region, some student will have trouble here. Now R mean is not going to be constant. If you draw it here, it's this much. If you draw it here, it's that much, right? So R mean is not a constant. If it's not a constant, then what you want to do is you're going to have to express the R mean in terms of the other polar coordinates, which is theta. So you got to find a certain kind of function. It's going to be a function of theta here. So let's see how we can find that function. We make use of whatever available at here. But first step, what is the definition of theta, right? You got to be very clear with that. And definition of theta is from x-axis to where? Okay, to wherever the line that you draw, the reading lines that you draw there. Okay, so that's your theta, right? Okay. All right. So I'm gonna maybe draw a separate one in here just to demonstrate the idea of the theta here. Okay. Yeah. So let's make use of the available one. What's available? I have a root 2 here. That's a constant. That's available here. Which part is root 2? This is a root 2, right? So from here to here, and that much of a length is root 2. And the other one I could make is I have a right triangle here. You see this right triangle? So this is your root 2 at here, and this portion is what? Is R mean we're looking for. And what's this angle here? Theta. Right. Very good. So I have theta. I don't care what theta is for now, but I'll treat it as variable. And I have the root 2. I'm looking for a relationship. Basically, it's a function of theta to express this R mean. So now, can you find an expression now for R mean using this triangle root 2 and theta? What would that be? Good. Sine theta equal to? Yeah. Okay. Yeah. Sorry. Sine theta equal to?
Root 2 over R.
That's right. So this is what I mean. I won't give you a formula like this, right? You know, you have to be able, at least these kind of fundamental ones, and I would expect that you have to know, okay? So if once you get to this step here, then your R mean basically is root 2 over sine theta, okay? So that's the, for this part here, there will be some similar questions, very similar questions, like finding R mean, R max, involving a right triangle with certain basic, staccato, that kind of relationship. Okay. Okay. So now, once you find this, it really doesn't matter. You don't have to express it as a cosecant theta. You don't really have to, but if you want to, that's fine. But it's optional. Okay. It doesn't matter. Okay. So once we find the R limits now, the next step is to find theta limit. Okay, finding the theta limits here. So, and then I got to emphasize that here the idea of the integration. As remember, when I do the review at the beginning, integration over region R basically means you have to scan through this region R, okay, without any redundancy. Now, this is our first step. Essentially we create a line segments like this, okay, but that's just a scanning through from here to here. So the next step, what we need to do is we basically rotate that reading line, this reading line L at here. Okay, and then from one end, the one end is very important. Okay, the one end is because that's your determinant theta here. It's always from one end of this region to the other end, counterclockwise direction. Okay, so in this particular case, you can see I have two boundaries, right? One over here, one over here. So we're gonna scan it through this region R from here to here. Okay, so scan that reading line through this region R to recreate or to basically cover every corner of the region R. Yeah. As you're scanning through, try to remember where the boundaries are. If this is first boundary, second boundary, then the theta mean, theta max are the corresponding limits or the corresponding angle value for the two boundaries at here. Okay? Yeah. So this is a second step at here, finding theta limits. In description, what we want to do is to rotate that reading line, okay, and across the region R, okay, or scanning through this region R. The two edges, okay, the two edges will give you theta mean and theta max. Okay. So if you look at this particular region here, let's look at the easy one here. So apparently the second edge is over here, okay, and theta is the corresponding angle, right, to that edge. So how do you draw the theta? It's always starting from x-axis, then you go all the way to the edge, counterclockwise. Okay? Yeah. So if I go from here to here, that's pretty simple, right? Which is what? Pi over 2. Okay? Yeah. And theta mean, okay, it's not so obvious, but you know where the boundary is. And the boundary basically is at from origin to that intersection point. Okay? So that's your lower edge. So then we would wonder, so what would be the intersection, right? So if I know the intersection point, then I would be able to calculate the theta mean. So that intersection point is the intersection between the circle and the y equal to √2. And it's pretty straightforward. If you substitute a y equal to √2 over here to the circle, what do you get? You get x squared plus 2 equal to 4. So x equal to √2. So that particular point has √2 coordinates. Okay? Then, which means the theta mean must be how much? So if you're going through here, √2, what will be this angle theta? Pi over 4, right? So 45 degrees. Yeah. So you get basically theta mean and theta max. Okay? Yeah. So after all, you can put down the limits now. However the function f is, we'll see an example next. Okay? So our mean is from here √2 over sine theta to the top, which is 2, the radius 2, and theta mean goes from pi over 4 to pi over 2. Okay. So that's the procedure, okay, for finding R limits and theta limits. Typical procedures. So you gotta practice a little bit sometimes. Okay, yeah. So let's take a look at an example. Let's integrate this function here over the following region R. So let's pick an easy region R for now. So first step, sketch the region R. Region R says within x squared plus y squared, so as y is less than and equal to 1. At the same time, keeping x and y greater than 0. So that basically means you are focusing on the first quadrant in here. And this is unit circle. So in short, we got ourselves a quarter circle at here for the region R. Okay, so now I'm going to integrate this function now. So we're trying to integrate this function. Okay. Before we do the integral here at this stage, let me break it down to sort of smaller pieces. So if you look at the formula for double integral, not only you're going to determine the limits, right, for the integration, you also have to do a proper substitution for the function f. Substitute x with r cosine theta, and substitute y with r sine theta. So let me do this step separately at this stage. So f replaced with r cosine and r sine. Here's my function f at here. I'm going to replace x with r cosine and replace the y with r sine. Okay. Very basic scale. And then you do a little bit of simplification. So this is r square cosine theta square and r square sine theta square. And you get a common factor r square here, and you take it out, you got a cosine theta square plus sine theta square. Again, this is my expectation. This is a very simple formula. You got to remember this kind of thing, right? So 1 minus r square. That's the that's the function f. Okay, become 1 minus r square once you do the substitution for these two expressions. Okay. So now I will find the limits. Now we're integrating 1 minus r square, and then r dr d theta. So don't forget this portion here. Okay, so this is a part of the formula. So r dr d theta. Finding limits, let's follow the steps we have just illustrated. So how do we find the limits? We start from origin and we draw a reading line out of the origin. Okay. The first contact gives us our mean, and the second contact gives us our max. So in this case here, what's the first contact? 0, right? It's right here. Okay. It's already in contact. Okay. When you start it, it's already in contact. Second contact is right on the edge of the circle. It's a unit circle, so the r max is 1. Second step to find the theta limits is you rotate this reading line, okay, across this region R. So find the edges, and in this case here, one edge is the bottom here, the other edge is at 90 degrees over here. So theta limits will be 0 to pi over 2. Okay. Yeah, so that's very straightforward. Then the rest of the job is basically a double integral, just like a Cartesian now, because you're just integrating the internal inside integral, and then integrate the outside one here. Okay? And there's really nothing tricky over here. So if you do it carefully, you get pi over 8, okay, for this question. Okay. Any questions so far? Okay. Oh, no. Okay, let me just maybe quickly go over this. So the inside integral here, you get 1/2 r squared. R times this is r, right? And then 1/3 r, no, not 1/3, 1/4 r to the power 4. And then r's limit is 0 to 1. Okay. If you calculate this, plug 1 into r and 0 into r, and you get 1/4 here, yeah. And then you get, this is pi over 2. Right. So 1/4, 0 to pi over 2, and you get pi over 8. Okay. All good? Yeah. Okay. So let's have one more simple exercise at here. But I'm going to give a different region R here. Okay. Okay, here is a different region R. And region R is basically the region sandwiched between two circles. It's part of the ring right here, and also above x-axis. Okay, so that's your region R here. Okay. Now, if I'm going to integrate this double integral at here, so instead of integrating using Cartesian, okay, integrate using polar, okay, and first step, replace y with r times sine theta. dA is become r dr d theta. And second step is to find the limits now. Finding limits, meaning we draw a reading line, okay, out of this region R across the region R. First contact give you R mean. Second contact give you the R max. So can you tell me what's R mean, R max at here? A and B. So A to B. And the next step is to find the theta limits. So you rotate these reading lines across that region R and find the two edges. Okay. After you do the rotation, this is very straightforward. So you find one edge in the positive x-axis direction, and the other edge is in the negative x-axis direction. So that basically 0 to how much? This is still very simple integral here. You will get 2 over 3 b cubed minus a cubed. Okay. So I would ask you to try out, okay, the two integrals, even this one here. Okay, I would ask you to try this integral out. Instead of using polar, use Cartesian. But I don't want you to finish, okay? I just want you to set it up and to feel how difficult it's actually going to be if you wanted to calculate this integral in Cartesian coordinates. Okay. And it's doable, but it will turn out to be much more a challenge process in terms of computation. Okay? Yeah. Now this is actually one of the reasons that at this stage now you learned Cartesian, you learned polar, right? So the question always is, you got to ask yourself, when you have a double integral, if the question didn't ask you specifically integrate using polar, then you had to ask yourself, what should I use? Should I use Cartesian or should I use polar coordinates, right, for this double integral? The rule of thumb is always, if your region R, okay, is somehow a sort of a involving a circular kind of region, okay, then chances are you should use polar coordinates. Okay. If it's some kind of a rectangular or triangle, okay, probably Cartesian coordinates. Okay. But bottom line is, if you tried it out, one turns out to be too challenged, then you probably should try the other, right? Yeah. And I always tell the class, you can try. If it doesn't work, doesn't mean the question doesn't work. But probably just means you use the wrong approach. Especially later where there's another topic, it's very similar. It only works this way, but not works the regular way. Okay, so just remember the possibilities out here. Okay, any question regarding this polar coordinates out here? Yeah. So the trick is always finding the limits. Okay, so now the next topic is, let's look at a general idea of so-called change of variables, or coordinates. Coordinates is a very arbitrary math definition. It doesn't mean you always restrict yourself in a Cartesian x and y, or restrict yourself in a polar r theta, right? You can mathematically, you can literally create any coordinates you want. Okay? There's a rule, but you can create any coordinate you want. As a matter of fact, you can pick up any a pair of two variables. Instead of x, y, let's pick a u and a v. Let's pick a w and a z, right? If you pick two variables, you can create a coordinate system. Okay? Yeah. So now question here is, if I don't want to do this double integral, okay, in using x or y, I can literally use any other two variables. Okay, that two variables could be used to create that new coordinate system, right? So as we just learned, basically you have an x changing to r and theta, and you have a y and change to r and theta, right? That's a transformation. Okay? Yeah. Now, in general, okay, you can change your x to another pair of basically coordinates uv, and you can change your y to another pair of coordinates u and v. Okay. So that's what we call the general change of variable right here. Okay. Of course, the challenge comes with, if I change the x, y to another pair of coordinates variable u and v at here, so what should I do with this double coordinates, the double integral? And for simplest, I can change the x to apparently to whatever the relationship uv, y, and uv, so that's fine, right? That can be a direct substitution. Okay. However, just like the polar, right? I need a du dv now instead of a dx dy. So what's going to be right in front of this du dv? Okay. It's like there should be a scale. Okay. It's essentially, if you recall that when we derived the polar coordinates formula, we got an r at here, right, in front of dr d theta. Okay. So now if I choose u and a v, I should have something here, right? It's not just going to be a 1. Maybe it's a 1, I don't know, but it's a question mark. So the following basically is to show you the general formula. How do I find a question mark at here? Right? So what we do first is we define a so-called a coordinate transformation vector. Okay, it's a fancy word, but really, basically, just you put these two functions in a column vector here. Okay, yeah. I'll show you an example next here. Right now, it probably just seems too abstract. What is x uv? What is y uv? Right? It's just an expression. Just like here, x equal to r cosine theta, y equal to r sine theta. Just a certain function. Now we'll put this into a column vector here. And now next, we have our useful Jacobian matrix. And you're learning it in numerical analysis, right? Yeah. And we only deal with 2 by 2. Okay, so don't worry. The Jacobian matrix is formed by using this basically coordinate transformation vector. It's very, very simple. You calculate a few partial derivatives. The first row are the partial derivative of x with respect to u and the partial derivative of x with respect to the v. And the second row is partial y over u and partial y over partial v. So that's Jacobian matrix. Okay. So once you get the Jacobian matrix, then you will calculate the determinant of the Jacobian here. So it's a 2 by 2, and I think you don't need to have the formula for that. Okay. So that's the Jacobian determinant. Symbol-wise, sometimes you'll see in some reference they use this particular symbol. Okay. Really, but not necessary. It's not required for this course. Okay. So if you see this symbol, that actually means that's the determinant of the Jacobian value here. Okay. Yeah. Once you get the determinant Jacobian, the question mark at here. Okay, so that question mark over there is basically the absolute value of this determinant of the Jacobian. Okay? So I didn't provide you the proof. Okay? If you're really interested in the proof, actually the proof is actually quite interesting. If you're really interested, and I'll show you a paper, maybe a 40 years ago paper actually, to show you how this is basically the question mark here is the determinant here. Okay? So in general now, this change of a variable, okay, give us the following formula here. X will become uv, y also be replaced with a certain expression yuv, and then here you need to calculate the absolute value of this determinant of the Jacobian. Finish that with the du dv. Okay. And there was integral over a region R. But this time, okay, this R is not going to be actually the same R anymore. It's going to be a R prime right here. Okay, it's going to be R prime. So the idea is, to simply put it, is like this. This is your Cartesian coordinates, and this is your dA, right, in the Cartesian. Okay. Now, this time here you have a UV coordinates. Okay. And then in the UV coordinates, you will have, I'm not going to draw this, so it's very hard to see, but maybe you're going to have a patch, okay, in the UV coordinates. It's okay, right? Now, for this one here, right, basically between this dA and this du dv, there is the scale. Basically, when you do the mapping from this coordinate system to the other coordinate system, okay, it's like a mapping right here, transformation. Then there needs to be a scale, which is the absolute value, the determinant of the determinant of the Jacobian right here, to be applied. Okay, so when you match from here to here, you need to have that determinant of the Jacobian here, okay, to connect these two patches, okay, in the two coordinate system. So that's basically the idea. But why this, right? Why this absolute value, that needs a proof. That needs a rigorous proof there. Okay? So if you're interested in that proof, and I can show you. Okay? Yeah. But the actual proof will be beyond this lecture here. So let's give you a simple example here. Let's use the polar coordinates to demonstrate. This is our polar coordinates, right? The relationship between Cartesian and polar. So if I try the formula and apply it to this polar here, Jacobian is the 2 by 2 matrix, partial x, partial theta, partial r, partial x, partial theta, partial y, partial r, and partial y, partial theta. So first row, you get a cosine theta here, and then you get r sine theta here, negative. Second row, you have a sine theta here, and then r cosine theta here. So now, if I calculate the determinant of the Jacobian, so that's basically this times this minus this times this. So that gives us r cosine times cosine r cosine square minus become positive r times sine theta square. So overall, what do we get? We get r here, right? We get r. Okay. Now remember, the formula requires to have absolute value of this determinant. So you need an absolute value of this. But if you recall how the r is defined, how r is defined is what? From origin to wherever that point is, right? That's the distance. So the r itself is actually naturally what? Positive. So basically you get r here. And that's exactly the formula we have just seen, right? When you are using polar coordinates. It's r dr d theta. Okay? Yeah. So where do we apply this this change variable here? It's actually very useful. I'll show you one example here, okay? And you'll see where you can apply here. So let's say we have a region R, and this region R is given by fairly complex relationship. So here's the region R. So given by two expressions. The first one is 2x minus y greater than 1 less than 3. The second one is x plus y greater than negative 2 and less than 0. Okay. So if I going to sketch this region R, so this is sometimes not an easy sketch. It's doable. Basically, you get 4 boundaries here, right? One boundary is 2x minus y equal to 1, 2x minus y equal to 3, x plus y negative 2, x plus y equal to 0. So you got 4 boundaries at here. You just need to draw the 4 straight lines, okay, in the xy coordinates. And if you draw them out, okay, this is a very rough drawing, and you can take a look at lecture notes for a really good drawing here. So you're gonna get a diamond kind of region here. Okay. So it more or less looks like this. Okay, so that's the boundaries of this region R. If you plot it out, you got 4 straight lines, okay, and you got a boundary set here. So if I'm going to integrate a certain function, let's say I'm going to integrate 3x dy dx. Okay, let's integrate this guy here. if you have not learned change of variable, and if you look at this double integral, you look at the region R at here, and I think your choice probably the Cartesian coordinates, right? You're probably not going to use polar coordinates. Okay? And if you use Cartesian coordinates, and if this dy dx is the order of the integration, then as we have done previously, you're going to draw basically arrow lines, okay, across this region R, okay, and then finding y min, y max, and sweep it and find x min, x max, right? Yeah. But the problem here is, at least you probably will notice right away, if I draw it here, I got a y min, y max, that's fine, right? But if I draw it here, got a y min, y max, so different, isn't it, right? Yeah. So this is actually going to be the next topic here. If I don't use change of variable, if I use the Cartesian coordinates, then apparently just one draw, right, from here to here, that's not going to cover all the scenarios. You at least have this one in here. So what do you have to do? If you keep on going with this Cartesian coordinates, you're going to actually have to divide this region R into two regions. Okay? You integrate through the half region first, and then you integrate the other half region. So that's basically like integration by pieces. Right? So this idea of integration by pieces is almost everywhere. The line integral, you have, if there are two lines, you integrate by pieces, C1, C2. Right? In single variable, it goes from A to B and B to C. And here, you can R1, R2, you can integrate right through these two pieces. Okay? Yeah. So that's what we're going to cover next. Okay? Yeah. However, since we're learning change of variable here, let's see how change of variable can significantly reduce this kind of difficult level of difficulty here. Okay? Now, the change of variable idea is you want to make this computation easier. Okay? Now, what's so difficult here is because this region R is kind of irregular here, right? It's not a rectangle, it's not a circle, right? If it's a very square rectangle, then things are easy. So we want to basically transform this into a simpler case. So I'm going to let u equal to 2x minus y, and v equal to x plus y. Yes?
For this question, isn't what you're doing dx dy, not dy dx? With the lines?
With the way I draw here, you mean?
Yeah.
I wrote down here dy dx.
And
right?
aren't what you're doing dx dy?
No, if I wrote down dy dx, the first step I draw is arrow line in the y-axis direction, right? And find y min, y max. If I write dx dy, then I would draw in this direction here, in the x-axis direction here. Yeah? Is that good?
Yeah.
Yeah. So, get back to the change of variable. Basically what I just did is, I'm letting u equal to this, and letting v equal to this. So you can immediately see, if I use a u equal to this, v equal to this, then uv as a pair of new coordinates, the region for u and v, this is constant for u and v, right? If I draw it in uv coordinates, and basically I will get v is between -2 and 0, and u is between 1 and 3. So what do I get? I get what? I get this region here, right? I get this region, okay? For u between 1 and 3, and v between -2 and 0. Okay? Yeah. Now this is a very nice region, right? If I integrate double integral within this region here. Okay. So that's the idea, right? We choose two variables, okay, u and v, to be like that. We create a new region, integral region, in the uv coordinates. And now the rest of the work is we have to apply the formula for this Jacobian double integral here. But first thing what we have to do is, right, we have to find out the x, y relationship with u and v. Okay. So this is our the u here equal to 2x minus y, v is this. So I can solve these two equations, treating u and v as a constant, solving for x and y. So 1 plus 2, you can solve for x, which is 1/3 u plus v. And solving for y, you get similar to 1/3 negative u plus 2v. Okay. So now this is basically your x uv function. This is your y, right? Become a function u and v. So I create next. We'll create this Jacobian matrix. Partial x over partial u, partial x, partial v, partial y, partial u, partial y, partial v. Very simple partial derivative. You look at this expression, you get 1/3 here, 1/3, and negative 1/3 here, and 2/3. Then you calculate determinant of this Jacobian. So this times this minus this times this, and you're going to get 3/9, which is 1/3. Okay, it's already a positive. Okay. So going back to the formula for the change of variable. Okay, so change of variable here, basically this original. Here's my original. Is it the original here? Yeah. This is original double integral here. And the new double integral here, okay, is in terms of u and v now. You're going to replace the x with what? 1/3 u plus v. And you replace the dA with this determinant of j, absolute value here, then du dv. Okay. Now, it's not the original region R anymore. It's that's the beautiful rectangle area in the u and v. We call it R prime. So I'm going to put everything together. Determinant of j is 1/3, and then du dv. Okay. And the limits for u and v is determined by this new region R prime. So this is R prime here. It's fairly self-explanatory. So basically u is between 1 and 3, and v is between -2 and 0 here. Yes. Huh? The other way around, but I let u equal to this, isn't it? Oh, the drawing is wrong? This is u, this is v, isn't it? Oh yeah, you're right, of course. Yes. What am I doing here? Excellent. Good job. By the way, yes, actually I cannot just arbitrarily change u and v. They had to have this right-hand rule, right, as the coordinates. So this is 1 here, this is 3 here. And this is -2 here. Good job, yeah. Like that, right? Yeah. Good point. Okay. So now putting the limits here, so u is between 1 and 3, v is between -2 and 0. Okay. So as you can see, this is a very simple double integral, right? There's no challenge, no mystery here. So you can calculate this without any difficulty. End up with the number 4. Okay. Yeah. as a matter of fact, the Jacobian, the idea of the Jacobian is actually nothing new. Just basically give you an idea of a Jacobian here. If I'm going to ask you to integrate this one here, let's see, right? If a single variable, integral 1 over 2x plus 1 dx, what's the technique you would use? Well, you probably know the answer, but if I really break it down to the details here, use substitution, right? This is basically one of the techniques for the midterm. So substitution, basically you let u equal to 2x plus 1. Okay? Yeah. Letting u equal to 2 plus 1 basically means x equal to u minus 1 over 2, right? Yeah. Then substitution basically becomes, for this one here, this becomes 1 over u, and dx here becomes what? Dx over du times du. Okay? Yeah. Now that's substitution. So you see here, this dx over du at here, what is this thing? This is basically the Jacobian we're just talking about here, right? That's the 1D Jacobian. Okay? And dx over du here you can calculate. For this particular case you can get it, which equal to 1/2. Okay? So that's your Jacobian basically. Okay? Yeah. So what we just cover here is essentially 2D Jacobian. And there's definitely higher dimension Jacobians there. Okay? The idea of Jacobian matrix, I'll give you a heads up. When you learn third year electrical, there's a probability course. So right now you're learning probability of single variable, and then there's a probability of multivariables. Okay, and the multivariable, and there's always double integral involved. The change of variable in that particular sense involving Jacobian. Okay, yeah. In robotics, if you recall that the demonstration, calculating inverse kinematics also requires the Jacobian. And Jacobian matrix is also involved in sometimes in the optimization. So this is a very useful concept here. Okay? And Jacobian is also involved in the linearization. So it's almost everywhere. So I think I'm running out of time a little bit. I'm going to cover the last question at the beginning of the next lecture. So any questions so far? Okay. Yeah. I'll see you next. No, see you Thursday. Yeah.